Hi everyone, my name is Karan Gaikwad. Welcome to the week 3 project presentation for advanced structural mechanics. The topic for the project is defining a scalar, vector and tensor field on your composite body. The composite body I've chosen is a table lamp, which is a combination of a hemisphere at the top and then two cylinders, one as the connecting rod and the second larger one as a base. Coming to the hemisphere, the parameterization for the hemisphere is similar to that of an octant. So I've generated the hemisphere by rotating the octant 4 times. This you can see is the calculation for the Jacobian of the hemisphere, which comes out to be r square sine phi, which is discussed in detail in the previous project video. We use this Jacobian to calculate the volumes for the surface for the bodies. So this is the volume calculation for the hemisphere. Coming to the cylinders, both of these cylinders share the same parametric equation. The only thing that is varying here is the radius, which is r for this cylinder and 2r for this one. Similarly, I've calculated the Jacobian for the cylinders as well, which I've used to calculate their volume. Coming to this week's project agenda, that is a scalar field. The scalar field for my body is basically given by x1, x2, and x3, which is basically x1 times x2 times x3, a function of the coordinates of the body. So in the figure, you can see these blue values represent plus 60 for all the positive values of the function, and it is minus 60, which is represented by this yellow patch for all the negative values, and 0 at the center where either of the coordinates are 0, so the function turns out to be 0. Coming to the vector fields, the vector field I've plotted is pretty simple. It's similar to the plot of y equal to x that is shown by this graph right here. The first one here displays the displacement in the x direction. The second one represents the displacement in the y. And it is 0 in the z direction because there's no displacement in the z direction. The arrows here represent the direction of the vector field. The color profile here basically displays the magnitude of the arrows. So you can see it is around 8 for this yellow patch, and it is minimum for the bottom of the half of the surface. The displayed figure in this picture is basically, if we imagine this vector field as a displacement field, so this is what the displacement profile would look like. On the next slide, this is basically the vector field that Professor Prakash has used in his video. So I've modified that vector field to work on my composite body. So this is what I came up with. So this curve is similar to the curve of 1 minus cos x. So the displacement profile you could see here is similar to 1 minus cos x up to pi by 2. So this seems to be a bit more practical and realistic as compared to the previous one. So I thought that I should include both of them. Coming to the tensor field, we are asked to plot a symmetric tensor field. So the one I've chosen is pretty simple. Again, it's basically a function of the coordinates, that is x1, x2, and x3. This you could see is a plot of the tensor field on the body. For calculating the effect of the tensor T on the vector U, I have selected the points 1, 2, and 11 with the radius as 4 and height as 3. So I've substituted all of these points into the equation, into basically this equation right here, so as to get the coordinates of U, which come out to be 5.133 minus 5.133 and 0. And then using matrix multiplication, I've multiplied matrix T with U to basically get TU, which comes out to be this. So this result I have obtained is similar to the result given by MATLAB here. Coming to the last slide, this is basically my MATLAB code for calculating the scalar, vector, and the tensor field. You can pause the video and have a look at it. That's it for this video. Thank you so much for watching. Have a good one.